Hello everybody, this is Dr. Christopher White and welcome to part 3 of Streams and Flooding. Alright, so we were just discussing discharge, and what you can see in front of you here is a stylized discharge diagram for a river over a period of 1 year. So what you'll notice is that, well, we're actually going to skip the winter, we're going to start in the spring. Spring tends to be when a river will very often have its highest rate of discharge. That's obviously because we have quite high amounts of rainfall, and it's also combined with a period of time where if we have had any snow or ice in the area, that will begin to melt, allowing the water to enter the river system. So typically spring is the highest discharge, or the peak discharge should I say. As we move into the summer, you'll see discharge begins to drop, and then we'll get a bit of a rise, and that's because as you're typically heading from May into June, normally your conditions will start to get drier, so the discharge will drop, so there's less water in your river. But then as you start to hit late summer, as you start going into July, kind of August, that's when you start hitting the periods where you're going to start getting thunderstorms. So that's the time of year when you might start seeing your discharge shooting up, often in a slightly more sporadic way, but you will see your discharge as a whole increase. Then you'll exit that period, you'll then start heading into early fall. Then you'll see the discharge start to go up in the fall, because once again it's a period where typically we will experience higher rates of rainfall. And then we will move from the fall into the winter. You'll notice the winter actually has the lowest discharge of all the seasons. And that's normally because a lot of rivers will not get the water because it's being locked up in the form of snow and ice. And so that water's not going anywhere, and so it cannot enter the river. Also, another situation is the air temperature will tend to drop. And so what you will have noticed is that when the air temperature gets low enough, it actually impedes cloud formation. And that, if it impedes cloud formation, obviously that will actually then impede the formation of rain. So you have to bear that in mind as well. So the winter is actually not a great time for precipitation, because the cooler temperatures tend to limit the possibility of clouds forming. And that then combined with the situation where if any precipitation does occur, if you're in the right climate, it can be locked up as snow and ice. And so that water won't be released until the spring. So that's just something to bear in mind. Okay, so let's have a look at something a little bit more local. All right, so let's look at the Brazos River. And so what can we see? All right, well, first of all, this is January here, and this is going to January over here. So essentially we have a whole year. Now, this is going to be for our area, so of course this is going to be slightly different. The Houston area does not suffer from a build-up of ice and snow which melts in the spring. So what do we see? Well, we can see that the discharge is actually relatively constant across the entire year. If you took an average line, it would come somewhere through here, wouldn't it? The only time when the discharge gets noticeably different is during the summer months, and we all know why that is. The Houston area and the surrounding area of southern Texas is of course prone to very, very big thunderstorms. And so what we tend to find in the summer months, that's when we tend to get the largest and most powerful of all the thunderstorms occurring. Obviously, we expect to get a peak in precipitation in the spring and fall months. That's kind of to be expected, because we expect during those time periods for the amount of precipitation to go up, because that's when it tends to get a bit more rainy naturally. And in the winter, well, the winter in the southern Texas can be variable. Sometimes it can be wet, sometimes it can be surprisingly dry. But nevertheless, the most important thing to note for our area is that the precipitation goes up typically in the summer, and so that's when we start seeing the highest discharge. And we can see the same thing here if we look at this graph. So we have average rainfall in inches. As you can see, as we begin to transition from spring into summer, this is when we start seeing a real peak in the rainfall. As we start moving into the September, October, November period, this is when we start seeing a more chaotic atmosphere. So if you remember, so for the Houston area, what tends to happen is we tend to just get a big area of high pressure ends up sitting over southern Texas, and it just keeps the entire area hot, stupidly hot. And then what happens is as we start to head into September, October and November, we start seeing lower pressure and colder air moving into the area, and that will start to naturally trigger rainstorms. And so that helps to explain why we're seeing this increase in precipitation in the September, October, November period. Okay. Now, just for comparison, this is the discharge diagram for a place called Ensham, which is in the United Kingdom, and it's the village in which I went to school. And so what can we see? Well, to start with, this diagram isn't quite as helpful because it doesn't start at January here. It's actually starting in October. So what you'll notice is we have the fall coming into the winter, coming into the spring. And the one thing you'll notice is in the UK, you can quite clearly see there's a big increase and slow drop off because the winter and because the fall, the winter and the spring all tend to be relatively wet. So we tend to get quite a lot of rainfall in these areas. So we get this big, broad curve. Compare that to more southern Texas, where you tend to get the summer is, this big pronounced peak because we tend to get a whole load of rainfall being dumped at just one time. In the case of the area of Ensham in the UK, you can see the rainfalls being spread out over a very, very long time period. When we come over here into the summer, what you'll notice is the discharge drops off, as you would expect, because it naturally gets drier in the summer. Although, let's face it, it's the United Kingdom, it doesn't get that dry. But every once in a while, you get these spikes, which are sporadic summer thunderstorms. So the discharge curve for Ensham in the UK is a lot simpler, and it's kind of as you would expect. The UK is on the whole quite a wet place, and so in the spring, the winter and the fall you would expect quite large amounts of rainfall, which we can see due to this big, broad, higher discharge region over here. And then we see the lowest discharge in the summer, but we see it gets quite sporadic because we get these, every once in a while we'll get these big thunderstorms causing the discharge to suddenly shoot up and then drop back down again afterwards. Alright, so let's start thinking about stream processes now. So here we have a very stylized diagram for a stream. You can see the stream's going to start off up here towards its headwaters and it's heading towards its mouth down here. Now, the one thing is remember, our river wants to achieve a nice smooth profile. So it wants to achieve a profile that looks something like that. And so, well, how is it going to do this? Oh, well, it's going to do it this way. So think about it. Here comes our water. It's moving along. It's quite happy. The slope's quite gentle, so its energy is relatively low. And then all of a sudden, it starts to drop faster. And so as it starts to drop faster, what's going to happen? It's going to increase in energy. As it starts to increase in energy, its ability to erode increases. And so all of a sudden, because the water starts to move faster, it has more energy, we're going to start seeing erosion here. And over time, the erosion is going to move this backwards and backwards and backwards and backwards until all of this area here above the red line is eroded away. Okay, so what's going to happen over here? Well, this area, the water's moving very, very quickly. It starts eroding. So all of a sudden, it's picking up extra sediment. Okay, so the river comes, lost the pointer there, sorry. The river comes hurtling down here, and then all of a sudden it hits this point where the gradient suddenly changes from steep to shallow again. And so all of a sudden your river loses velocity, and so what does your river do? It starts to deposit sediment, it starts to dump it. And so what will happen is over time you'll smooth out this profile by eroding material up here because the water starts moving faster, and depositing material down here because the river has essentially a change in velocity. It goes from fast to slow, meaning that material is deposited down here. And so you will move towards this perfect red line scenario. And that's how a river helps to essentially smooth out its profile. It will erode areas of steepness and get rid of them. And if there are any kind of depressions, it will naturally fill them in over time. And of course, this is just a direct reflection of the Hallström diagram, which we've seen several times before. So remember, as the velocity increases, the capacity of the river to erode also increases. So as the velocity gets higher, it can start eroding larger and larger and larger stuff, both coarse material and fine material. On the other hand, as your velocity starts to drop, it will start depositing material with the coarsest stuff first, and then steadily as the velocity gets lower, finer and finer and finer. So not really a huge shock there. You can probably you probably work that one out for yourselves. So obviously we need to think about, well, how does a river actually erode? Well, a river will tend to want to achieve what we would call equilibrium. So it wants a nice balanced situation. And so that's the characteristic of the concave up longitudinal profile, which is the perfect profile the river wants to achieve. Once it achieves that profile, it is happy, for want of a better description. Essentially, rapids and waterfalls have been smoothed out and eroded away, and if there's been any kind of depression, that's been filled in by sediment. And so what you have at this point is you have this delicate balance between the available sediment load and the transporting capacity. So the river has essentially achieved equilibrium, and that is exactly where it wants to be. The next type of situation we can have is what's referred to as headward erosion. And that's the slow uphill growth of a valley above its original source by gullying, mass wasting, and sheet erosion. That essentially means that the river is cutting upwards, uphill, towards where the water is coming from. So if we just jump back to the previous slide, or previous slides 2 back, you'll see this erosion, as we start eroding this area here and we start moving backwards towards where the water's coming from, this is headward erosion. We are getting rid of this material here, and we are eroding towards the head of the river, which is going to be somewhere up here. The final type of erosion is referred to as lateral erosion. And lateral erosion is what happens with meandering rivers. So if you think about it, a meandering river does not really have the capacity to erode down because it's quite a low energy river. So what ends up happening? Well, what ends up happening is the river, instead of eroding downwards, it starts eroding sideways. And so this will mean the river will swing across the floodplain. Essentially, well, the river will move from side to side, essentially producing the floodplain. And so what you end up with is this big flat area, which we call the floodplain, and that's the area across which the river will move laterally. And then it will typically have high ground either side, which is above the floodplain. Okay, so those are our two main types of erosion that a river will produce. Headward erosion towards the river's source, and lateral erosion associated with meandering rivers, where the river will move from side to side. So in terms of headward erosion, how does it actually work? Well, as discussed, the river will start to erode towards its headwaters up here. So headwater erosion essentially is the process of deepening a valley by erosion of the stream bed. So remember, these rivers in these high gradient areas have lots of energy. So they don't erode from side to side, they erode straight down. And so we can see in this diagram here, here's our river, and it's gone and eroded straight down. Now what this means is you end up producing this essentially this void here, which means the rocks here and here will naturally become unstable because there's nothing supporting them because it's been taken away. And so this material will naturally fall into the river channel and be transported away. This means that what you end up with is a distinctive valley shape which has a noticeable V morphology to it, otherwise known as a V-shaped valley. And this is the classic type of valley you get in areas with quite high gradients. So what's going to happen is over time the river will slowly erode backwards, up and up and up towards the headwaters using this process. It will steadily cut down, material will fall in, and as you can see the valley steadily gets wider as it moves upwards. Now one of the things we need to remember is any type of erosion cannot go past the base level. Okay, so a river can't erode below its base level. It's nearly impossible. All right, so we need to bear that in mind. So, you know what, just let me go back for 1 second. So base level is very often sea level. However, if there's something like a lake, so if we have a lake down here instead of the sea, the base level would be the lake level instead. All right. So in this situation we have lateral erosion. Lateral erosion is caused by the meandering river having these meanders, these curves in it. And that means as the water moves around the meander, it has to speed up on one side and slow down on the other. So just to show you, here's our meander. Okay, the water moving on the inside, because it's got a shorter path, slows down. The water that's flowing around the outside of the meander, because it's got a longer path, has to speed up. As the water speeds up, more velocity. More velocity equals more energy. And so on the outside of the meander here, it's going to steadily erode away and eat into this ledge here. And it's going to slowly pull the river this way. So the river's going to slowly move that way. And what's going to happen is you're going to get erosion on this side of the meander. And because the water's slowing down here on the inside, you're going to get deposition. And so the river will slowly move this way. And eventually the river will start moving back. It'll go backwards and forwards and backwards and forwards across the floodplain over long periods of time. So here you can see this is that situation. Here's a lovely example from Argentina. You can actually see all the old meanders from where the river has been flowing in the past. And so this entire area here is the floodplain. And so you can see over time the river's been moving across the floodplain backwards and forwards and backwards and forwards and backwards and forwards. And you can see the same kind of thing here. So this is the Amazon River in Brazil. It's a bit more difficult to see because obviously it's so heavily forested, but you can see these sweeping shapes in the vegetation here. These are the old meanders. Once again, showing you the river's been migrating backwards and forwards across its floodplain. So meandering rivers will move laterally across their floodplain. They will not erode downwards because they don't have enough energy. So if we focus in on meanders for just a second and we have a look at how the velocity is distributed, this is the situation. So let's look at this very simplistic diagram here. On the outside of the meander, the water moves fastest, so that's where we have the highest energy and therefore the ability to erode the river's banks. In contrast, on the inside of the meander, the water will naturally slow down, and that is where we'll get deposition taking place. So if we look at this diagram, this photograph down here, okay, of the Arkansas River in Colorado, what can we see? Well, we can see, look in the insides of these meanders here, 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 and here. You can see this area has kind of got this kind of yellowy cream material. This is fresh sediment that's being deposited in the core of the meander, and it hasn't been covered over by vegetation yet. In contrast, on the outsides of the meanders, here, 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 and here, you can see there is no sediment being deposited. That's because this is where the water is moving fastest, and it's actually eroding into the banks. There, 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 and there. So over time, the river is actually going to accentuate these meanders. They're going to become even more extreme the longer they exist. So why does a meander actually exist? Well, a meander actually only exists because there will be a very, very, very slight kink in the original path of the river when it first formed. And so it will just be something super, super small, like a little variation in the river channel. But over time, that variation means the water on the outside moves a little bit faster, and the water on the outside here, here, and here moves a little bit faster, and on the inside here, here, and here, it moves a little bit slower. And so over time, this little kink in the river channel starts to get accentuated and accentuated and accentuated over time. And so, given enough time, your meander becomes more and more extreme. Notice though, on the insides of these meanders, as the meanders migrate, they will leave sediment behind them in the core of the meander, and that will eventually get covered over by sediment, by plants. So as your river migrates, as your meander migrates this way, it might erode here, but it deposits material around itself here. It's in a kind of equilibrium almost. It'll deposit fresh material behind itself as it erodes material in front of itself. Eventually what will happen is the meander will become so extreme that the meanders will nearly touch, and eventually they'll erode through. Okay, and this process is sometimes referred to as decapitation, because what happens is your river channel then cuts through from there to there. The channel here and here gets filled in by sediment, and you're left with what's referred to as an oxbow lake, which is something, once again, you may remember from high school geography. So how are our rivers actually eroding material? Well, a river will erode material through one of three main processes: hydraulic action, solution, and abrasion. So hydraulic action is relatively straightforward. That's simply the ability of flowing water to pick up and move rock and sediment. That's it. So it can, if there's a loose piece of rock, it'll pick it up and take it away. It can then move that piece of sediment, it can pick it up, and it can slam rocks down as well. Okay? But most hydraulic action is just simply picking up and rolling rocks along. The next type of erosional process is solution, and that's just simply dissolving the rock. Now, we've discussed how that happens. Essentially, the minerals in the rock just essentially break into their ions, and the ions dissolve in the water. So that's relatively straightforward. Then we have abrasion. So abrasion is a physical process. It's produced by the clast being rolled along the bottom of the river. As the clast rolls along the bottom of the river, it slowly wears down the riverbed. Just like how huge trucks driving along a road, over time they'll slowly damage the concrete or the asphalt. It's the same process. As the rocks just roll along the riverbed, they slowly grind it down. There will also be the process of saltation, where you've got clast being lifted up and then dropped onto the riverbed again. So that's the impact process as well. Will also help to grind away, erode the riverbed. So a river will erode through hydraulic action, solution, and abrasion. So here we have a few diagrams, nicked straight from the textbook. So in this instance, we can see what processes essentially erode material. So we have moving clasts collide with each other and obstacles, chipping them away. So essentially an abrasive process. We have turbulence loosens and lifts pieces of the stream bed. So that's hydraulic action. And we have solution, so we have materials dissolving and being taken into solution. Essentially the ions moving into the water. In terms of how is material transported and deposited, well, fine material is obviously transported in the water. That's the silt and the clay. Sands and gravels will obviously be transported as part of the bed load. Soluble ions are transported within the water. So two variables that we have to think about when we think about rivers are capacity and competence. So the capacity is the total volume of sediment the stream is able to transport within both the bed load and suspended in the water. Now, obviously, the capacity will increase during times of flooding and high discharge. The more water you have in your river, well, obviously the more sediment can be suspended in that water, and the more water you have in that river, the more energy that water has as well, so the more sediment it can erode and carry along as part of the bed load. The other variable is something which is referred to as the competence. That is the maximum size of a clast that a river can move. Well, once again, the higher the discharge, the more water you're trying to squeeze through a confined space. So just think about it. If you have a normal river and it's got a normal flow and everything's fine, well then all of a sudden you have floods. You have a load of water that wants to come down your river very, very quickly. The river channel suddenly can't get wider. And so what does that river have to do? Well, the only thing it can do is it can increase the velocity, can't it? It can try and push that water through the channel much, much faster to get it done. And so what this means is, because the velocity starts to increase, the size of clast which it can transport will also increase. And so you'll see rivers in flood, where they're trying to squeeze a lot of water through an area as quickly as possible, you will see the competence will increase very, very quickly. And that leads to situations like this, where we have very, very large floods, where literally whole houses can be picked up by the flood waters and transported away. Excuse me. I shouldn't have coughed into my hand then, that was very bad form. Then we have deposition. Well, deposition will occur at base level or at or near the stream's end. So when the river, the stream, whatever exact process you want to describe it as, comes to a near complete stop, that's when we're going to get most of the deposition. Now, you will get deposition obviously when there's also a change in velocity. So we've discussed how, if there's some kind of topographic low and the river wants to smooth out that low, it will deposit sediment into it. That will tend to be rather minor though. The vast majority of the sediment will tend to get dumped at the river's end most of the time. So sometimes sediment can be deposited inside the river channel itself. You can see in this rather low resolution image here, you can see you have these bodies in the river channel. These are referred to as river bars, and these are temporary features. They are, as you can see, they're not vegetated. That's because they won't be around long enough to be vegetated. They're typically made of quite coarse material, quite loose material, sands, maybe gravels, and they will be eroded away over time, and essentially that material gets transported away, and a new bar will build up somewhere else. So areas where we tend to get quite large amounts of deposition, areas like alluvial fans. Well, obviously in this situation we have a river heading down this mountain canyon, and you can see it comes to its base level, which in this case is the desert plain. Now please notice all of these evaporites here. So this is actually a player lake, so it is in theory a body of water. It's a transient one though, it doesn't last very long, but it is there. So as the water comes down here, it reaches its base level, which in this case is the player lake, and that's where we get all of our deposition here. In terms of deltas, well, once again, that's another situation where we have a river meeting a large body of water, an ocean, a sea, a lake, and the water essentially slows down, loses velocity very, very quickly, and it has to dump that sediment. And so, once again, a delta is another situation where we have our water essentially hitting its base level. Now, a floodplain is a situation where the river is very near its base level. It's not quite there, but it's very, very near. So in this situation, the water's slowing down, but every once in a while there'll be essentially a period of very high discharge, and the water will have to go out of the river, and that's because the gradient is relatively low, so you can't push that water downstream very, very quickly because the velocity is naturally not that high. And so the water just exits the channel and floods the surrounding area, depositing the sediment as it goes. The water will then recede back into the river, and the sediment gets left behind. So this diagram here just kind of summarizes the base level concept. So as discussed, your river wants to achieve this perfect concave profile, and it will do that through eroding material and depositing material. Now in this case, the ultimate base level for this particular river is going to be the sea. So that's going to be base level right here. But what you can see is as the river is progressing along, there is actually a lake in the way. And so this will be what's referred to as a local base level. And so the river from this part upwards will use this local base level to produce its concave profile. Whereas south of the river, or below the lake here, south of the lake, below the lake, you will see the profile will use the sea as the base level. Now, what will eventually happen is, given enough time, either this side of the lake here will weaken and the lake will catastrophically empty, in which case the lake's lost. When the lake's gone, then the river, all of the river will try and erode towards this nice concave profile with the sea as the ultimate base level. Or the other option is, maybe over time the lake will completely silt up. It will fill up with sediment, so it will no longer be a body of water, it will just be, just a body of sediment. And once the body of water is gone, well, once again, the lake's no longer there, so it no longer forms a local base level, and so the ultimate base level becomes once again the ocean, and the river will try and achieve this perfect concave profile. So, given enough time, the river will essentially change its profile. Essentially, it will normally be able to use the sea as the ultimate base level. So, when a stream approaches its base level, well, what do we get? We've already discussed this. We get deposition. All right, so here's the Nile. You can see the Nile Delta right here. We've obviously got lots of deposition here. That's because the waters of the Nile are hitting the waters of the Mediterranean Sea. The river is slowing down as that impact occurs. It's losing velocity, and it has to dump sediment. You will also notice that along essentially along the floodplain in the Nile right here. You'll notice it's also vegetated, and that's because this is the area where you are getting some sediments deposited during flooding. But you will notice it's nowhere near as much sediment as is being deposited here in the delta. Here's another situation where we have ourselves another nice delta. This one's a bit clearer. You can't really see the channels inside the delta, but you can see them very nicely here. So here's the delta itself, and within the delta you can see you have these very, very fine rivers cutting across the delta. These are called distributary channels, not tributary, distributary, because they're distributing the water. And so these distributary channels transport the water across the delta. In terms of deposition within the river itself, as we discussed, we have these things which we call bars. And these are normally bodies of sediment, typically loose sediment, so sands and gravels. They get deposited in the middle of a river stream, in the middle of the stream. So why are they depositing there? Well, typically, let's say your water has some velocity. Okay, so it has some velocity, and then it's transporting all this stuff. It's got clay and silt and sand and gravels, and it's doing really well, but then it starts to lose a bit of velocity. Well, when it starts to lose that velocity, it has to dump the gravels and dump the coarse sand. So it dumps them in the river channel itself. And these sediments getting dumped in the river channel itself will form these bars. Now, obviously, as you can see, the river erodes in between the bars, kind of like producing these isolated little islands. And over time, because these bars are made of very, very loose material, they will be eroded away. The next time the river starts to increase in velocity again, all this loose material gets picked up and it gets transported downstream. So in terms of what we see, here are two main types of river: braided on the left, meandering on the right. What can we see? Well, we can see in the case of the braided river, we have multiple channels all running in the same direction, and you can see within the channel itself we have lots and lots of these bars. Remember, they're temporary bodies, they will be eroded away. But even then, you can see this kind of river does have a floodplain. You can see it there. And so the river will be moving from side to side over time across this floodplain. Now, it doesn't need to form meanders to do this. That's simply because all of this material here on the floodplain is so loose and poorly consolidated that the river doesn't really have to worry about, meandering from side to side. It can just punch its way through because the material has no consolidation. So essentially on this floodplain here, the river just takes whatever path it wants rather than meandering across it. In the case of the meandering river over here, you can see we have the meanders, so we now have one narrow, deep channel. You can see we have these nice curved meanders here. As we've gone and discussed, on the outside of the meanders, we have erosion. On the inside of the meanders, where the water is moving slower, we have deposition. And you can see the deposition in the form of these creamy sediments here. Okay, you can see them in the core of all of these meanders, there, etc. And you can also see as we move from side to side, the floodplain starts over here and comes all the way over here. And in this case, the floodplain is being formed by the river, essentially moving laterally backwards and forwards across the floodplain, and it's doing this by lateral erosion, which is produced by the meanders. Okay, so this is a good place to stop part 3, and so we'll move on to part 4. So once again, take some time, have a walk around, drink some water, cup of tea, cup of coffee, relax for a few minutes, and then come back for part 4, please.